One of the maddening things for cosmologists, perhaps the most maddening thing actually, is that there is a hard limit on just how far back we can currently look regarding the Big Bang. Sure, we can see its afterglow in the cosmic microwave background radiation, the CMB, but the real problem is that there is a brick wall there that prevents us from seeing before a certain time in the history of the universe, because before that moment, which was about 380,000 years after the Big Bang, everything was opaque. That didn't clear until everything expanded and thus cooled sufficiently for the universe to become transparent. There still weren't any other light sources in the universe other than the CMB at that point. That took a lot longer for the first stars to form, but at least it was transparent, made so by the universe cooling sufficiently for it to move from a ridiculously dense, hot soup of particles that photons had little chance of not immediately getting absorbed, indeed all hitting each other with such force that any atoms that tried to form were instantly broken apart, to calm and cool enough to form hydrogen and eventually helium, a little lithium, until eventually clumping occurred and the stars began to light up, after enough time passed for their materials to accumulate so they could ignite their fusion furnaces. But the CMB dates from that 380,000 year mark, and that's the earliest thing we can currently study. And within it we can see temperature differences that would eventually yield galaxies and clumped matter. However, there was something else in the universe that actually was released immune to all of this, known as decoupling and free streaming, about 1 second after the Big Bang, that could go quite a ways further in demystifying what happened directly after the event. It's the notoriously non-interactive neutrino. The problem is it's extraordinarily hard to detect neutrinos because it's one of the most non-interactive things we can currently detect, which is why it could move freely around the early universe like that when photons could not. This is the hypothesized cosmic microwave neutrino background, one of the great budding fields of cosmology, and also currently probably the single most fruitful thing we currently know about as far as figuring out the Big Bang. It could be a treasure trove of information on how all of this came to be, if we can figure out a way to study it. The non-interactivity of the neutrino, it's basically an identified particle of a type, some class perhaps of dark matter particles, is actually necessary here. Non-interactive means that it didn't care if the universe was opaque. It just cruised on through anyway, oblivious to the hot soup of particles compacted around it, carrying primordial information of the first moment after the Big Bang, the first second ever. Now, we already study neutrinos. There are some sparse interactions that they can do, and giant detectors of water and ice can detect the flashes of eerie blue Cherenkov light related to that. So we can see them occasionally, but not quite in the way needed for the primordial background. So the neutrinos we see are predominantly from the sun, plus several other sources, and we see them only because they are high energy. The background neutrinos are not high energy, and that's the problem. So conventional thinking on neutrinos is that you build your giant water detector. One of them is sitting at the bottom of the Mediterranean Sea, and another under the Antarctic ice sheet, and you look for high energy neutrinos. One thing to remember here is that photons have no rest mass. This is why they travel at the speed of light. They have nothing inherent to them to slow them down. Neutrinos do have mass, and there are 3 kinds of neutrinos, all with tiny but existent different masses. That means that they travel at different speeds, all slower than light, and show a time profile as a result. Like everything else, gravitational sources bend their paths. They gravitationally lens. But because they travel at different speeds and photons do not, you get a sense of time from neutrinos that you don't get with photons. Another interesting aspect here is that while we have never directly seen a primordial neutrino, all of Big Bang cosmology points to them being there and having been generated. And there are hints of them, even in the CMB. But say we never found them at all, despite developing and employing certain hypothetical detectors. This would be amazing in itself because it would point to a serious problem with cosmological models of the Big Bang and evoke rather exciting new physics and insights. A null detection here is just as interesting as a detection would be. But how to search for something with a hard-to-detect signal made even harder to detect out of weakness than the already difficult-to-detect solar neutrinos? One idea exploits an unusual, if rare, interaction a neutrino can have with an atom. If a neutrino hits an atomic nucleus just right, it can get captured and thus impart energy to the atom, causing one of its protons to convert into a neutron. The result is that it turns into another element entirely. That would be detectable, no problem, and there would be only one mechanism for it, that it was hit by a neutrino, but it needed to be high energy to do that in the first place. Primordial ones don't have the energy for this. In 1970, this was put to the test with a tank full of a very chlorine-rich solution. If one of the atoms of chlorine got hit and turned into argon, then that would be detection. The only problem was that a cosmic ray can also do this too. So to compensate, the experiment was located in a gold mine in South Dakota, far underground, which should have filtered out the cosmic rays because those do interact and rock stops them. This allowed the team, Davis and Pakal, to net a Nobel Prize, because using that method allowed them to measure the rate of neutrinos flowing off the sun. But this is a lot harder with primordial neutrinos. But there was also another idea, starting in the 60s, that was a kind of variation on this theme. Steven Weinberg, another Nobel laureate, looked into tritium, which is unstable. So tritium, which is radioactive hydrogen, decays, and when it does, it emits an electron at a known energy level. So the idea was that if a primordial neutrino is absorbed just before decay, the resulting electron should come out at higher energy than normal. But this effect would be very weak, and the experiment difficult, on the order of 100 grams of tritium releasing 4 neutrino-assisted electrons per year, which made the experiment impossible to perform when it was devised. Today, it may be possible, and there are plans to try to build a prototype detector. There are other ideas. The problem with most of them is that the precision of measurement is so high that it would be hard to reach at current technological levels, though maybe not in the future. There are other ideas regarding using the atmosphere to detect rare interactions from primordial neutrinos, but the problem is you'd have to continuously look for centuries to have any hope of seeing it. But there is an interesting possibility. So the primordial neutrinos are traveling at weak energies. So if your detector is just sitting there like our current neutrino detectors stuck under ice or water, it's not likely to see the weak interactions of very old neutrinos. Not so with higher energy neutrinos, but primordial ones. It's below the threshold. But there may be a hack proposed by Martin Bauer at Durham University in the UK. This idea comes at it from a completely different angle. Instead of the neutrino weakly hitting the atoms of your detector, here you're ramming the atoms of the detector into the neutrino. That should amplify the signal. Getting atoms to move really fast is hard. We need rockets and legs and wheels and orbits and things like that. But to get them up to large fractions of the speed of light, you need a lot of energy. The problem is that the easy ways of accelerating something usually involve electromagnetically accelerating them. And with atoms in their normal state, it's hard to get them up to crazy speeds. Not so if you start stripping off electrons and the atom becomes ionized. Then it becomes much easier to accelerate with electromagnetism, and indeed, we already have the technology for this, no problem. It doesn't matter if you hit a neutrino with a full-on atom or an ionized one. The effect will be the same, so in principle, you can use a particle accelerator to speed up a large number of ions to very high speed, meaning that the primordial neutrino streaming through the detector might eventually get hit by an atomic bullet, and the right detector could pick it up. Trouble is, if you go with previous experiments involving the chlorine, you need a very large particle accelerator, far larger than we have. This gets into energies where you need an infeasibly large accelerator, so it's dead in the water. But there are ways to use ions of other atoms to reduce the energies needed, such as a helium atom, which would whack the primordial neutrino that's been happily wandering the cosmos for 13.8 billion years without unfortunately running into humans, or rather the deadly helium ions they are making, and voila, according to Bauer, out would pop a converted atom to tritium, easily detected. But you still need an accelerator 100 times more powerful than the Large Hadron Collider we have now. That's within the realm of a future accelerator. Each generation of those we build, they get bigger. And the next one might reach this level, probably easily. It would probably need to be designed with this experiment in mind, as you need a lot of atoms for this, more than usual for an accelerator. And there may even be ions that could be used that will produce a hit signal at lower energies to make this a bit more efficient. But this is a glimpse at future physics, because the payoff of making a detection of primordial neutrinos would be huge, flagship-level science in the not-too-distant future. A few decades, really. And from there, if you find them, you have ways to figure out how to characterize them and get your peek at the first second after the Big Bang. Thanks for listening. I am futurist and science fiction author John Michael Godier, currently gearing up for a busy February. Had a rough January for several reasons, but now both here and Event Horizon are back on track and somewhat backlogged with videos, so will be a lot of them this month. It'll be fun, and be sure to check out my books at your favorite online book retailer and subscribe to my channels for regular in-depth explorations into the interesting, weird, and unknown aspects of this amazing universe in which we live.